So we are basically discussing the compactness of a space. A topological space X is compact if we discuss one result that a topological space X is compact if and only if for every collection C of closed subset of X having the finite intersection property. That means whenever we take finite subcollection of C, its intersection is non-empty. That is finite intersection property. So whenever collection C of closed subsets of X having finite intersection property, its total intersection is also non-empty. So there is this result, which is equivalent condition of the compactness. So we discuss Lebesgue number lemma that says that whenever we have an open cover C of a sequentially compact matrix space. So sequentially compact matrix space means in which every sequence has a convergent subsequence. So such a topological space which is matrix space and in which we have an open cover C, then we can always find a positive number delta such that whenever we take a set whose diameter is less than delta, we will always get a the set U in this family C such that B is contained in U. So whenever we have a set V whose diameter is less than that particular number, we can always find a open set U containing B. So that is this Lebesgue number lemma. And one more result we discuss, which is in terms of totally boundedness. So a matrix space X is totally bounded if for every epsilon, whatever small enough epsilon we have, we can always find a finite collection of all epsilon balls in that matrix space which covers the entire space X. Then that matrix space X is known as totally bounded space. So this this lemma says that every sequentially compact matrix space is always totally bounded. So let us see what kind of example, what is the meaning of totally bounded set. So if we take X is equal to R2, so that is a matrix space, and in which if I take a set A, which is a rectangle in R2, and what is given is we are given a positive number epsilon. So one length is given, that is we call epsilon. That is a fixed positive number. So we are going to consider the epsilon balls. That means whatever length is given, we'll consider the open disk with this particular radius. So question is A are totally bounded? Matrix space. So matrix space means subspace means A as a subset of R2. It is also a matrix space. So whether we can cover the rectangle A by epsilon balls, finitely many epsilon balls. So solution is we can give geometrically. So whatever rectangle is given, let us say, for example, this is my rectangle. So this is my A, which is a rectangle. Now one length is given. So for example, let us use some another color. So one length is given. For example, this is my epsilon. So that means we have a epsilon ball around a particular point, which is, so this will be basically the epsilon ball at a particular center A, center X. The question is, can I cover X by finitely many such balls? So we can see easily, yes, we can cover. So for example, I take any point in this set. So let us say this is my point x1. Whenever I take epsilon ball around x1, that will cover basically this part of the set A. So now I want to cover A by finitely many such balls. So that is we can easily see that that is possible. For example, x2 if I take here, then this is another epsilon ball with center x2. Then I can take x3 here. So I will get another epsilon ball centered at x3. For example, here I can take x4, then x5, x6, x7, let us say here x8, right? And in case here any point is left, we can take x9 here and cover that those points also. So basically the idea is that I can cover A by finitely many points x1, x2, x9 in this particular case. But even I take epsilon small enough, still I can find a number of points which will be the center, and we can cover the whole rectangle, right? So that means basically what we have shown here geometrically is that A is a totally bounded subspace of R2. But the whole space R2 we cannot cover by finitely many such balls. For that we need infinitely many such balls to cover R2. So that means R2 is not totally bounded metric space. Okay, so this is regarding that totally boundedness. Now today I want to discuss the converse of result which we proved earlier. So earlier uh, we proved that every every complex matrix space is sequentially compact. So today we will discuss the converse of this theorem. So let XD be a matrix space. So if this matrix space is sequentially compact, then we will show that X is X is compact, right? So to prove this theorem, we use the two main results. One is the Lebesgue number lemma, and second we will use this every compact matrix space is totally bounded. So this result we will use here. So let us start with because we want to show that this matrix space is compact. So by definition, we need to show that every open cover contains a finite subcover. So let us start with open cover X. So let C be an open cover of the matrix space X. So that means what? That is, I can write X as a union of open sets U, where U is element of this open cover. So this is given, and what we want to find is we want to find a finite subcover of X, right? To show that X is compact. So for that, let us start with the Lebesgue number lemma. So by Lebesgue number lemma, matter basically it is length. So there exists delta greater than 0 such that whenever for every subset B of the matrix space X such that the diameter of B is less than delta. So once we have a diameter is less than this positive number, then what we get is there exists a element of the open cover such that B is a subset of U. So this is exactly the total boundedness. For instead of epsilon, we are considering uh, we are instead of epsilon walls, we are considering delta walls, right? So basically, what we are getting here is that we are getting delta walls. So once we have this Lebesgue number lemma, then what we'll do is that we can choose some particular number depending on delta. So now I'm calling a positive number epsilon, which is this given delta by 3, right? Because delta is positive number, so epsilon is equal to delta by 3 is also positive number. So now so here we use actually this Lebesgue number lemma here. So Lebesgue number lemma, we have actually used delta itself, that whenever we have delta greater than 0 and set with diameter less than delta, we have open set U belongs to C such that V is subset of U. So that is what we have written here, and now we are applying the total boundedness. The total boundedness, what is given is we have for any positive number epsilon. So this epsilon we are choosing in terms of this particular delta, that epsilon is delta by 3, and now we get this conclusion that we can cover X by finitely many epsilon balls. So the example which we discuss, the same way we can find x1, x2, xn and epsilon balls centered at those points which will cover the entire space X. So for this particular epsilon, by the totally boundedness, so we can apply totally boundedness because we have a sequentially compact space. So we are using the hypothesis. So by the totally boundedness of X, uh, we get n epsilon balls centered at x1, x2, xn such that it will cover entire X. So that means we can uh, write X as a union of these balls. So bx1 epsilon, then another ball centered at x2 radius epsilon, and so on, union b xn epsilon. So we got X basically is covered by n epsilon balls, but what we need is that we need to show the compactness, we need X is covered by finitely many open subsets of the open cover. So now from this epsilon ball, we need to go to the open set of the family, right? So for that, we will use basically the Lebesgue number lemma. So to use the Lebesgue number lemma, what we need is that we need a set with diameter less than delta. So note that the diameter of the ball psi epsilon. So this ball centered at xi and radius epsilon has radius epsilon. So its diameter will be 2 times epsilon, right? So the diameter will be 2 times epsilon, but in case if we take discrete topology, then diameter can be less than also, right? If there is only singleton elements. So in that case, the diameter in fact is less than equal to 2 epsilon, and then we know that we have chosen a specific epsilon, that is delta by 3. So since epsilon is delta by 3, delta is equal to 3 epsilon. So 2 epsilon is less than equal to 3 epsilon, which is delta. So now what we got is that we have a set whose diameter is strictly less than delta, and then we can apply this Lebesgue number lemma, say that we have a set whose diameter is less than delta, so we can find a open set in the family such that this particular set is contained in the open set. So therefore, uh, so let us write down this property star. So therefore, by the conclusion star, there exist. Yeah. So basically, this is true for every I, right? So by star, for each I is equal to 1 to n, there exist. So for every ball center at xi, we get a open set. That open set we will call ui, right? So there exists ui in C such that this ball is contained in ui. Right. So finally, what we get is therefore x, which is union of I n from 1 to n, ball center at xi radius epsilon, is now contained in each ball center at xi is containing ui. So this is containing I running from 1 to n ui. So basically, x is a subset of finitely many ui, and ui is an element of the given open cover. So we have shown that x is every open cover has finite subcover. Of C, and therefore X is compact. X is a compact topological space. So we proved that whenever we take a matrix space X, then every The topological, the matrix space X is sequentially compact, implies compact, and if it is compact, then it is sequentially compact. So that means compactness and sequentially compactness is equivalent for the matrix space case, right? So, so now one more result we want to prove in the setup of matrix space and compactness, that is regarding uniform continuity. So uniform continuity means basically delta does not depend on the points. So let X be a compact matrix space and consider a function from X to R. So if you remember the result of real analysis, that if whenever we take a function on the closed interval AB which is continuous, then it is always uniformly continuous. So that is because the closed interval AB is a uh, compact subset of real line. So same way that result we want to generalize here, that whenever we take the domain which is a compact matrix space and we consider a function f from that compact matrix space to R which is continuous, then it is automatically uh, uniformly continuous. So then f is uniformly continuous. So to discuss this, first of all, we need what is meaning of uniform continuity, right? So F is uniformly continuous. So let us recall this definition. So that is meaning is that for every epsilon greater than 0, there exists delta greater than 0, such that whenever we have modulus x minus y less than delta, so here it is matrix space, so we will take distance of x with y less than delta. Then, so f takes value in real number. So now we have in the codomain we have matrix which is modulus. On R we have modulus. So fx minus fy is less than epsilon. So this we want to prove, that is basically meaning of the uniform continuity. So we want to prove that whenever we take a function whose domain is compact matrix space and that function is continuous, then that is uniformly continuous. So now first of all, let us note that we can always cover R by infinitely many. So R is not totally bounded because it cannot be covered by finitely many epsilon balls, but we can surely cover by infinitely many open balls. So for example, if we take the ball around every point of whatever positive radius, then we can always cover R by union of such balls, right? So around every point, whatever given point T, we are taking the ball of radius epsilon by 2. So that means every T is belongs to BT epsilon by 2. So that means singleton T is subset of this ball, and then we can take union. So that means union of singleton is R, is subset of T belongs to R. right? And the converse is always true. All these sets are subset of R, so that means basically we get this. So R we have covered by these balls, and each of these ball is open. So what is this ball? Basically, here we have the distance is modulus. So that means all x such that distance of x with t is less than epsilon by 2. That means mod of x minus t is less than epsilon by 2. So this is the ball basically. So R we can cover by yeah. So this is the diagram is wrong because we are not in R2, we are in R. So it will be interval actually. So this set is basically t minus epsilon by 2 to t plus epsilon by 2. So this is the ball basically. So we can always cover R by these balls, and then so now what we'll do is we will take the inverse image both the sides. So what we'll get is f inverse of R is the same as f inverse of union of t belongs to R, ball center at t with radius epsilon by 2, right? And then you apply f inverse. So then we know that f inverse preserves the union. So that means it is f inverse of centered ball radius epsilon by 2 and center at t. And then we know that each such ball is open, so f inverse of that is also open because f is continuous. And on the other hand, what is f inverse of R? F inverse of R is x, right? Because f is a function from x to R. So this gives us that x is, we can write as union of open sets. That means this is basically open cover of x, right? So so we got an open cover, and once we have an open cover, we can apply the Lebesgue number lemma, which says that there exists delta such that whenever we have diameter less than delta, we can find a open set containing that set B. So let us write down what we get from the Lebesgue number lemma. So by Lebesgue number lemma, there exists delta 1 greater than 0 such that for every subset A of x of diameter less than delta 1, there exists an element there exists an element of the open cover. So here element of the open cover is of this form, such that the given set A is a subset of this set F inverse BT epsilon by 2, right? So we are getting an element of this form that depends on T. So whenever we say there exists an element, that means there is particular T is there. So let us call this T fixed T by T naught. So we get this, and then in particular what we get is we know the diameter of the ball. So note that diameter of the ball center at x with radius delta 1 by 2 is always less than or equal to delta 1, right? Because radius is delta 1 by 2, so diameter will be less than or equal to delta 1. So finally what we get is that therefore so this result said whenever we have a set with diameter less than delta 1, that set is subset of f inverse bt naught epsilon by 2. So that means b of x delta 1 by 2 is a subset of f inverse t comma epsilon by 2, right? T naught comma epsilon by 2. And so, so so this is what we have. Now let us consider, uh, let us denote this delta 1 by 2 by delta. So just changing the notation, because finally in the uniform continuity we need some positive number delta, so that delta is basically delta 1 by 2, right? So now using this particular equation, what we get is that, let us take some element in this delta ball. So this means what? That is x minus y is sorry, distance of x minus y is less than delta, right? Because x and y are elements of the matrix space capital X. So whenever this happens, we take any element in this set, it will also belongs to this set. Y belongs to f inverse of T naught epsilon by 2. So that means what? If y belongs to f inverse of the set, that means f of y belongs to. So did I forget something? Yeah, I think I forgot to write the ball here. So ball center at t0 and radius epsilon by 2. So f of y is in this ball, and that will give us that now this ball is in the real line, so that means it is a neighborhood. So that will give us f of y minus t naught is less than epsilon by 2. So finally what we get is, whenever we take any element y in this ball, when y is in the ball center at x with radius delta, we get f of y minus t naught is less than epsilon by 2. So in particular, every element x belongs to the ball center at x, right? So in particular, x belongs to this ball. So we get, so just substitute y equal to x. So what we get is f of x minus t naught is less than epsilon by 2, right? So the distance of fx with t naught is less than epsilon by 2. The distance of fy with t naught is less than epsilon by 2. That means the distance between fx and fy is less than epsilon. So therefore we get distance of fx minus fy. So By triangle inequality, this is less than equal to fx minus t naught plus fy minus t naught, and each of these is less than epsilon by 2. So that means fx minus fy less than epsilon. And what is the condition between x and y? X and y are in this delta ball. So that means distance of x and y is less than delta. So whenever we have, so finally what we get is, therefore there exists delta greater than 0, which is delta 1 by 2. Yeah. So we should start with, for every epsilon greater than 0, there exists delta such that whenever distance of x with y is less than delta, we get distance of fx and fy is less than epsilon. So this will give us that, therefore f is uniformly continuous. So basically this the proof that every continuous function on the closed interval is uniformly continuous, we have extended it for the compact metric space using totally boundedness and Lebesgue number lemma. So these two things we use here. So this is regarding regarding the sequentially bounded species. So let us just discuss one definition. Then I will stop the lecture maybe. So, so a topological space X is called limit point compact if every infinite subset of X has a limit point. So let us see one example. So consider A to be the set 0 to 1 as a subspace of R with the standard topology. So R with the standard topology, this is a particular subset of R. So question is that is a limit point compact space. So for limit point compact space, what we need to check is that whenever we take an infinite subspace of this topological space, it has a limit point, right? And basically we know that one of the limit point of this set is 1, but it actually does not belong to this set. So therefore this set is not limit point compact set. So solution is that, so consider the infinite set one minus one upon n belongs to n in A, then this set has uh, no limit point in A because its limit is basically 1, which is not in A, so therefore A is not a limit point compact. So to show it is limit point compact, we need to check for every infinite subset of the metric space, of the topological space. But to show it is not limit point compact, we need to check for only one infinite set, and we have to show the limit point does not belong to the given topological space. So I think this is enough for today lecture.